Share my screen. Okay. So here's the setup we're going to be using. Excuse me. For today's lab. And again, we're working on induction machines. And the concept of an induction machine is that, excuse me, it's a machine that you have to go ahead and operate it at below synchronous speed if it's operating as an induction motor, and above synchronous machine or synchronous speed if it's operating as a generator. So we're going to connect this in a Y configuration. So here's our induction 4-pole squirrel cage induction motor. I have my 4 leads coming in for power. I connect these as a Y. I ended up using the 3-meter method to go ahead and calculate these. You can use the 2 that's shown on the sheet, or you can just do the 3, which is I'm monitoring the current in each of the legs, and then the voltage is the voltage across each phase. And again, this is just brought over from phase to neutral. I'm also recording the torque as well as the RPM speed in my DAC, so I can actually use the data monitor to make that work. Okay. And then I'm going to go ahead and turn this up to full power. So I've got my setup where I'm gonna essentially, what I'm going to do is I'm just going to allow it to basically allow it to collect the data that I need, and then not have any load on it. And then I'm going to go ahead and vary the load, but I don't want that to vary as the voltage changes. Okay. So the first test we're going to do with the 4-quadrant, whoops, wrong button, sorry about that. With the 4-quadrant dynamometer is we're going to set our torque to 0. And then we're going to go ahead and set our data logger up so that I'm monitoring each of the voltages, because I'm using the 3-phase connection, each of the currents, my torque and my speed. And then I'm also recording, because I'm using the 3-phase connections to get the 3-phase power, it's P1, P2, P3 for real power, Q1, Q2, Q3 for reactive power. If you're going to follow what is shown in the lab handout, make sure you put this as PQS1 and PQS2. All right. If you just put PQS1, you're only going to get the power from how the unit is connected on just phase 1. All right. I'll give you guys a couple minutes to go ahead and connect your circuit up. I'll get this out of the way and give you some time to go ahead and set that up. And tell me when you all have it set up or almost ready, or if you have questions. How are you making out? Any questions?
Almost got it.
Okay.
Yeah, me too.
Okay.
think I got it.
Okay, Braden.
Yep, I'm good.
Okay. All right, let's fire in the hole. And flip the switch. And now we bring up our metering window to show the speed, voltages, P and Q and all that stuff. So this right here is, if we bring up our control here, our setting for torque is equal to 0. So right now we have applied no torque to the unit. So for number 5, the no load speed of operation is 1775, which is exactly what we expect, right? We know it can't run at 1800 RPM, which is a synchronous speed for a 4-pole motor, but under very little load, and the load we can actually see, it's pulling at about 103 watts. So there are some parasitic losses because you've got some friction and windage. We have some I²R losses in the windings, but essentially there's no mechanical load connected to it. So this is about the maximum speed that you're going to see this unit rotate at. We do have a little bit of parasitic load associated with connecting the dynamometer on it, but it's pretty small relative to what happens. And if you put this at the corrected value, this kind of shows you what the torque would be spinning at, which is a pretty small number. So it's not outputting any torque, but it's still drawing about 0.598 to overcome some of the values. So for number 5, our speed is 1775, and it looks like it's rotating in a clockwise direction. Okay. So the question is the no load speed almost equal to the speed of the magnetic field, which is a synchronous speed? The answer is yes, because synchronous speed is 1800 RPM. This is spinning at 1775, which is only slightly less than the synchronous speed. So yes, the answer is that is what we expect.
I'm not getting that. All my voltages and currents and power are the same, but my RPMs is only getting up to 443.
Did you turn down the torque here to 0?
Yes.
And you can you share your screen so I can see what's going on?
What do I? Oh, it says host disabled participant screen sharing.
Sorry about that. I thought I had changed that. All right, try that again.
And I'll pull the meter onto the screen. Oh, this thing is not like that.
It's putting out, go back to the device. All right, can you bring up the 4-quadrant? There you go, yeah. Huh.
Oh, now it's
Go back to the diagram. I mean, to the actual circuit. Voltage is all the way up. Can you just double check that your torque and your speed are going to the right terminals?
yeah.
So that your torque is going to, I think it's AI 7, and your speed, your N should be going to 8.
Oh,
Nope.
my torque is going to 8.
Yeah, that's backwards. You got to switch those around. You're gonna have to delete it. It won't move you up there. So just delete it and then reconnect it.
All right, there we go.
All right. Braden, what are you getting for data?
I'm currently rebuilding because it froze when I got my last
Okay.
wire. So I had to go back and I couldn't get it to unfreeze.
Okay. Well, while you're connecting that, we'll see. Let me share my screen. What the next step is. So you're going to make the torque correction function, make sure that it's enabled, which means that this right here is for correction. So it's going to go ahead and correct it. To include, like I said, the internal losses. So you actually get what would be the equivalent demanded torque of that particular machine. Even though it's outputting 0, you're still pulling that value, the 0.6. The only way that get that to 0 is you'd have to remove the mechanical coupling between the two. Okay. So now I'm going to slowly increase the torque demanded until this reaches 175. So I'm going to start it. Oh, come on. And slowly increase that. Overshot it a little bit. Close enough for me. Okay. So now I'm going to record this data. So I'm going to record the nominal speed, 1747 RPM, the corrected value of torque in Newton meters, 0.961, and then my nominal current, 0.854, 0.855, whichever you think. And now I'm going to go ahead and turn that back to 0. Okay. And then we're on to step 7. You all following along?
Yeah.
Pat?
Yep.
Okay. So for this one, we're going to actually come up with torque versus speed characteristic. So we're going to vary our torque. We're going to start at 0, do a recording. Then we're going to increase it by 0.3 Newton meters until we get to 2.1. And then once we get to 2.1, we're going to increase it by 0.1 Newton meters until we're going to see some motor stalling. So the best thing to do is to set up your recording. So you're going to monitor voltage, the torque, one current, the speed, and the real and reactive powers for my system. Okay, so one voltage, one torque, a current, a speed, the real power, and the reactive power. And for your very first data point, you're going to actually record the data at, and I'm going to move this over here, at this value, because this is when my torque output is equal to 0. So I'm going to hit the record button, and that's my first value. Now I'm going to increase this to 0.3. And I'm going to wait just a little bit for this to stabilize out. So you got to give it a second to stabilize. And it stabilized a little bit. So I'm going to record my second value point and go here. Now I'm going to move this to 0.6. Give it a second to stabilize the speed and the torque. Everything looks pretty stable. I'm going to record that data. 0.9. Okay. So you're seeing as I'm increasing the torque, the speed is dropping exactly like what we would expect on the torque versus speed characteristic. Our real power is going up. Our reactive power is not changing all that much, but our line current is increasing because the motor is putting out more power. It's delivering more power to the load. So did I record this data point already? I have not. So let's hit record. Now I've got it at 0.9. Now I move to 1.2. Let it stabilize. Once it's stabilized, I hit the record and I'm good to go. And for what it's worth, if you look at the motor has a, zoom in quite a bit. The nominal full load speed of this thing is 1670 RPM. Actually, no, this one is 1500 RPM, or I think that's 1685. So right about now, we're almost delivering rated power output of the machine. We can continue to increase that, but keep in mind, once you run at higher than the nominal output torque, you are starting to potentially degrade the motor because it's running with more current than it's designed to. And it's running with less cooling. But this is a simulation, so we can do that, no problem. 1.5. Now we're overload. We're going to record that data at 1.5. Go to 1.8. Excuse me. Record that data. 2.1. Let it stabilize and record. Now we're going to go up in 0.1 increments because we're getting close to the pull-out torque, the maximum torque this machine can put out. So we don't want to make big jumps because we might overshoot our maximum value. So let's do 2.2. Stabilize. That looks pretty good. We're going to record. We'll do 2.3. Stabilize again. Pretty good. Excuse me. 2.4. That looks right about here. We're stable. Record. 2.5. $14.64 looks pretty good to me. All right, 63. So we'll record that. 2.6. And let's see, we're going down. The current is sort of stabilizing. Let's see, 14.19. Is that our last one? It looks like it's stabilizing at 14.19. So we're going to go ahead and record that here. 2.7. And you'll notice you're going to start to see bigger jumps in the speed dropping. So previously we went 1463 to 1419, which is around 50 RPM. Now we're going from 1419 to around 1350. So that's 70 RPM. So we're starting to get along that top of that curve where we're starting to see pretty big changes. So 1350 looks pretty stable. We'll go ahead up 1349. So we'll go ahead and record that. We'll go to 2.8. So now we expect it to be in the 1260, 1250 range, give or take. Well, maybe even a little off from there. But this one now has changed over 100 RPM. So hopefully it stabilizes. It's continuing to drop. Is it going to stabilize? It's getting... not really stopping. It just continues to decrease. So we might have gone past at the 2.7. We may have gone past because now you can just see it's starting to cascade. So we missed it. We missed the peak value of what it could be. So instead of doing the 2.8, I'm going to try 2.75 and see if I can get that. So let's go back up to, let's go to 0 and let's get it spinning at full load speed. And then I'm going to try 2.7. And hopefully that doesn't overshoot. And then once 2.7 settles down, if it can settle down, then we'll try 2.75 to sort of find that truly that peak value of where we can get. So this is just a little bit where we're looking at the data and we can see that we missed that peak point. So now we're trying to do it a little bit more slowly to see if the results that we can get are consistent and if we can actually get that almost peak output value. So we're waiting to see if it gets back to 1349, which was our speed. There we go. Now I'm going to change it to 2.75 and see if this gets us to our last sort of stable value. It seems like it's slowing down. We might have made it. It's really close though. We might have found it. Give it a chance to stabilize. Let's see, 1279. Is this the final one? Oops. This might be the very last value that we're going to get because remember when we went to 2.8, it just dropped off precipitously. So I think this is about the best we're going to do to find the maximum value of torque that we can get. So I'm going to go ahead and hit the record button because it was at 1279. It did go to 1278, took a long time. 1277 seems like it's sort of stabilizing out. You're not getting a huge amount of change. You also look at the powers. The power output really isn't changing all that much. You know, it's kind of bouncing around between 0.1 and 0.7. So the suspicion is this is about as stable, although it did go to a 0.2. This is probably about as stable as it's going to get. So I'm going to go ahead and record this, and then I'll move this up to, I'll move this value up to 2.8, and then we're going to see that at that point, we've overshot. So we're going to go ahead and just record what the maximum value will be. So here we go, hit my record button. And then I'm going to take this to 2.8, and we'll just see that it's going to drop, continue to drop until it gets to its speed. So we're just going to wait till it stabilizes out. And essentially what we're having here is what the starting torque, it would be a fairly flat part of the curve where no matter what the torque is, the speed is not going to change all that much because that torque is fairly constant over that range. So whatever speed we get, we're not going to get a huge change as we increase the torque. So essentially this next torque value that we're going to find is the torque that what we would consider its starting torque. Because again, it's pretty linear for the first little bit. So let's figure out a stabilizing point. And we're looking good right about here. All right, so now I'm going to take this to 0. Now, the reason why I took that to 0 is at this point, I want to allow my motor to cool off. And why I'm not shutting it down because in the real world, a machine running at very light load, which is almost synchronous speed, it's got a lot of air. So this induction machine is cooling itself off. So you don't want to shut it down completely because then it has all this heat that it can't reject to the atmosphere effectively. So what we're doing now is we're just going to let it cool. So we'll collect our data. So we're going to go ahead and export this. So we'll call this Lab 7 Wednesday. We'll export it. Then we'll go to Excel. And we'll open it up. And I want this to be all files. And then this is just comma separated values. So we'll bring it in like that. We're going to save it as an Excel spreadsheet because if we try to add graphs, it's going to give us some heartburn. So we're going to save it. And now we're ready to go ahead and do some data analysis. The first thing it wants to do is do a curve of torque versus speed. So I'm going to put my x-axis is going to be torque, and my y-axis is going to, I'm sorry, my torque, and then my y-axis is going to be speed. So I typically want my axes, my x-axis to be over here. So what I'm going to do is I'm going to move this and dump that over here. And then I'm going to delete this because actually what I'm going to do is I'm going to move this. I'll move this row over. Whoops. I'm going to move this data over to here. Sorry. I guess I have to cut it. And I'm going to insert it here. So now, because I'm going to go ahead and set up my x-axis is here, then all my parameters should go ahead and do it correctly. So the first thing I'm going to do is relabel these. This is my voltage. This is my speed. My torque. This is my current, my P. I'll put P total and my Q total. So now I want to do a torque versus speed characteristic. I'm going to select both those columns, and I'll actually include these titles because Excel is smart enough to figure that out. I'm going to do an XY plot, and that's my torque versus speed characteristic, which looks pretty darn close to the lab handout, right? You can see that at full load speed, or synchronous speed, I should say, which is 1800 RPM, I'm almost putting out 0. And then I start to go up pretty steep until I hit basically my pullout torque. And at that point, any more torque load just means that the machine speed is going to slow down. So I can't capture any of these data points over here because I would have to come up at it from this angle and see if I could get up to this point. Okay, so that is my torque versus speed characteristic that I'm going to go. And it's exactly as I expect. As I increase the torque, I decrease the speed until I reach my pullout torque. And at that point, it's going to basically, essentially hardly any output torque. The speed actually slows down and I can't produce any torque. Okay. And then the nominal speed of the unit is, you can put a little point. So we'll put a shape. Let's put a star. And let's see if we can put a star. And we'll shrink it down because it's too big. And we're going to put that down right at 1685 RPM. So I'm going to actually add in some minor lines. And let's see. That's the major. Minor. How come I don't actually see that? Okay. I don't know why I'm not able to show. I'd like to put in another one. That's the major grid lines. I want minor ones. Let's see. All right, so this is 1600, 1700, 1800. So someplace around here is where my full load output is going to be. 1685, pretty darn close to 1700. Okay. Questions on that?
No.
Doing okay so far?
Yep.
Okay. Now it says determine the breakdown torque, which is the max value. So even though we specified 2.85, it looks like our maximum value is right here. So our breakdown torque is just over 3. Actually, it's the one right next to it. Sorry about that. I highlighted the wrong one. 3.06 Newton meters is the breakdown torque. But our locked rotor torque is what the torque is going to be, because remember, this is fairly flat. So our locked rotor torque is this one, 2.289, or right around 2.3. Again, that's what the starting torque can be, and the pull-up torque is going to increase, and then we're going to be, our full load is going to be below the maximum torque for sure, but also before the starting torque, because if this value wasn't below the starting torque, then the machine would never start to spin. All right. Now, the next plot we're going to do is real power and reactive power versus our torque. So let's do here. And let's see if I can do those two. And it's not what I want. So let's do one. I wonder why it's not smart enough. I specified my torque. Oh, no, I want my speed. That's why. Sorry, guys. It's speed, not torque, versus P and Q. I was grabbing the wrong one. That's why it was giving me some heartburn. There we go. So you can select the two, and you can do speed versus torque. So this is versus power, not torque. Okay. So question. So the orange line is Q. It shows that as my speed, and remember, we started up over here, as my speed decreased, did my reactive power demand go down or go up? It's fairly flat, and then it starts to increase. So that tells me for my reactive power, it's always demanding reactive power as this machine operates. The power eventually will get to zero, especially if it's going at synchronous speed. But this thing pulls hardly any power here. But you can see it really doesn't do any less than the reactive power here, which is what we expect in an induction machine. All that magnetic energy that's needed in this machine to be able to operate correctly has to come from the line. So it has to take reactive power to feed the line. So the question is, does it always draw reactive power from the source? The answer is yes. And does it draw more active power? It sure does. As we increase the torque until we get to this breakdown value, our power increases. And you can see the power curve follows a very similar pattern or design as the torque versus speed characteristic. Okay. So the answer is yes, it draws more electric power when it draws a heavier load. And I think this is the last curve that we're going to do, which is speed. Oh, is there a question?
Oh, sorry. No, I just sneezed, forgot to mute.
Okay. So speed versus current. I'm going to insert my XY plot. And there's my speed versus current. So you can see at low slip values or very close to synchronous speed, it pulls hardly any power. Look how much power this unit actually draws at lower values. Way more current. So you can see why it's much smarter to run the machine over here It's going to draw less current. It's more efficient because again, I'm putting out full power over here. Over here, I'm not putting out the full power of it. I'm overloading it. And this is where I could actually get damaged. So I want to operate more efficiently over here. So the question is, how does the line current vary as the motor speed decreases? It increases. It almost increases linearly. As I increase my load, my current increases. Okay. So I increase my load, my current increases. As I decrease my speed, which is the same thing as increasing the load, my current increases. Okay. Nominal line current should be at exactly this same point. So if I copy and paste this over here, and again, I do my minor lines. So I'm going to add my minor lines. And I'm going to move this to 1670, which is right about here. That's the nominal current of the machine. Okay. So right when we hit about 1685, somewhere between these two, this is the nominal line current of the machine, somewhere between 1.53 and 1.8. Okay. That's it for data analysis. The last thing we're going to do is we don't need this. We will turn this is off. It's been spinning at no load for a little bit. So the last thing we're going to do is, and you can see these are spinning clockwise. We're going to stop the power and we'll stop the motor. And we're going to go ahead and swap out any of these leads. So temporarily, I'm going to pull that one over here. I'm going to pull this over here, plug that back, and let's see if our clockwise changes. So we'll flip the switch. And now we're running counterclockwise. Okay. So what's going clockwise? Now it's going counterclockwise. And we can do that with any one. So we swapped 1 and 2. So let's put 1 and 2 back. And instead of swapping 1 and 2, let's swap 1 and 3. So remember, it was clockwise before. Now we swapped 1 and 3. We're back to being clockwise, counterclockwise. So any two leads, because now it's spinning counterclockwise. Let's swap 2 and 3. Oh, that didn't change. Let's swap that back. Flip the switch. And now it's going clockwise. So for part 12, what is the direction? We had it going clockwise initially. When we flipped the switch, it went counterclockwise. So does the induction motor rotate opposite direction? The answer is yes. It goes opposite. And that's it for the lab. Other than the questions. So questions for me. Did you have any questions, Pat? I didn't hear you.
No, I think I'm all set.
Okay. Well, I'm going to pause the recording and then I'll stick around and answer any questions you have. Okay, I'll pause the recording.